The space-time reality of the universe can be thought of as a big, stretchy fabric. This fabric is what we call space-time, and everything in the universe, planets, stars, even light, moves through it. Imagine space-time like a trampoline. When you place a heavy object, like a bowling ball, which represents a planet or a star, on the trampoline, it creates a dip or curve. Smaller objects, like marbles, which represent smaller planets or light, move around the dip caused by the heavy object. This is similar to how gravity works. Big objects like planets bend space-time, and smaller objects follow those curves. So, space-time is both where everything exists and how everything interacts, bending and stretching depending on the mass of objects. The faster something moves, or the heavier it is, the more it changes space-time around it. This is why scientists say that time and space are connected. They're part of the same fabric. Space-time isn't like a physical medium such as fabric or rubber, and using analogies like a trampoline can be misleading. The reality is more abstract, but here's a simpler, more accurate explanation. Space-time is not a thing made of stuff. It's a concept that combines space, where things are, and time, when things happen, into a single stage where the universe plays out. Objects with mass, like stars and planets, affect this stage by bending it not because there's something physically there, but because space and time themselves change based on how mass and energy are distributed. Imagine the universe as a kind of invisible grid. When nothing is in it, this grid is flat. But when you put something heavy, like a planet, into the grid lines curve around it. This curvature is how gravity works. Objects follow these curves naturally, which is why planets orbit stars. Even though there's no physical material in space-time, the presence of mass and energy changes the way objects move through space and how clocks measure time, giving us the effects of gravity and time dilation. So, space-time is more of a mathematical framework describing how space and time behave together rather than a physical substance. Although space-time is a concept, it's grounded in physical evidence and can be proven through observations and experiments that match predictions made by Einstein's theory of general relativity. Einstein predicted that massive objects like stars and galaxies would bend the path of light because they curve space-time. This effect, called gravitational lensing, has been observed many times. During a solar eclipse in 1919, scientists measured starlight bending around the sun, confirming that space-time curvature affects light, as predicted. Time dilation, or how clocks run differently, is a fascinating aspect of Einstein's theory. The theory says that time flows differently depending on how strong gravity is or how fast you're moving. This has been confirmed using very precise atomic clocks on Earth and in space. For example, GPS satellites need to account for the fact that time moves slightly faster in orbit, where gravity is weaker than it does on the Earth's surface. Without these adjustments, GPS systems wouldn't work properly. Einstein's theory also explains small details in the motion of planets. The planet Mercury, for instance, has a wobble in its orbit that Newton's gravity couldn't fully explain. General relativity accounts for this wobble due to space-time curvature near the Sun. In 2015, scientists detected gravitational waves for the first time. These are ripples in space-time caused by massive objects like black holes colliding. The waves were directly observed by the LIGO experiment, which detected tiny changes in the distance between mirrors as the waves passed through Earth. This was a huge confirmation of space-time as a real, dynamic entity. Each of these examples demonstrates that space-time is more than just a concept. Its effects are measurable and match what general relativity predicts. Even though we can't see or touch space-time itself, its behavior has been observed through how it influences matter, light, and time.